Let L be the line that is the intersection of the planes x plus y plus z equals 3 and x minus y plus z equals 5 in R3. An equation of the plane that contains 0, 0, 0 and is perpendicular to L is one of these. Okay, so this is pretty much just going to involve some vector geometry. So if I want an equation of a plane which is perpendicular to L, what I need is the direction vector of L. So suppose, how should I write this? Let's call it, why am I zoomed in here? If I say the direction vector of L is equal to A, B, C, then the plane that I want is going to be given by equation AX plus BY plus CZ is equal to 0. So first I have to find the direction of the line L, and then we're just looking for this equation. So how do I find the direction of L? Well, L is the line which is the intersection of two other planes. So if I have two planes that intersect, this vector is going to be perpendicular to both normals. So let's say n1 is equal to 1, 1, 1. That's a normal vector of the first plane. And n2 is equal to n2 is equal to 1, negative 1, 1. Then any line, any vector in the first plane is perpendicular to that, and any vector in the second plane is perpendicular to that. And so if I want a vector, which is if I want a line or a vector which is in both planes, it's going to be perpendicular to both. Easiest way to find a vector which is perpendicular to two given vectors is to take the cross product. So d of L is going to be n1 cross n2. And now I get to remember how to do cross products. I used to have this formula memorized. I, j, k times 1, 1, 1, 1, negative 1. I'm looking for a determinant of that. So this is I times 2 minus j times 0 plus k times negative 1. So, no. K times negative 2. So this direction vector is 2, 0, negative 2. Or in fact, any scalar multiple of this will work. So the plane, if I replace that with 1, 0, negative 1, because again, I can take any scalar multiple of this, then the plane, the equation of the plane is going to be x minus z is equal to 0, which is option A. Okay, so this plane clearly contains the origin. If I plug in 0, 0, 0, we get equality. And we can, if we wanted to, we could check that the direction of this vector is perpendicular to the original, or the normal of this vector, which is 1, 0, negative 1, is perpendicular to both of the original vectors. That's pretty easy to see, right? Here's one of the vectors. If I take a dot product with that, I get 0. And if I take a dot product with that, I get 0. Yeah, so just understanding the geometry of the problem and the relationship between normal vectors and equations of planes was pretty much all that was needed to do this one. Yeah, if I have anything more to say, I'll write it down in the description. Thanks for watching.